Hi folks, in this lecture we are implementing on Matlab finite element code to solve truss structures. I assume you know the existence and how a truss structure is defined. A truss structure is like this one, so each element is linked to the others with hinges, so it's not able to transmit rotational moments. It can deform axially, it can also rotate, but it cannot bend. This lecture is very practical, so is devoted to people who already knows something about structural analysis and is very oriented to the writing of the code. This structure I am considering is taken from the exercise for the Feynman lectures on physics, is this one. The cover of the book, if you are interested, is this one, exercise for the Feynman lectures on physics. And I have created a very similar structure on Abacus. Then I wrote the input file to get these two matrices that are the matrices that I'm interested in. Now, of course, these two matrices, you can type them by your own, but since the structures has a lot of elements and a lot of nodes, I prefer to use Matlab to have a quick way to get these matrices. But of course, you can modify them, you can write your own matrices. Now I'm telling you what those matrices are. In the first column you have the number of elements, the number of nodes. So for example, this row is defining node number 4. In the last two columns you have the x and y coordinate of the node. On the second matrix you have the number of the element. So for example, this row is defining element number 10, and in the last two columns you have the nodes that are composing the element. So for example, element number 10 is composed by the linkage between node 8, whose coordinates are this, and node 7, whose coordinates are this. If you are typing by your own these two matrices, the first column is not mandatory, of course. Since I'm using the one that Abacus is providing, I will carry on also the first column, but I mean, it doesn't matter. So the first matrix is this one. Let's put it in Matlab. And the second matrix is the matrix of the elements. Sorry. That is this one. And copy to Matlab. Okay, so first thing is let's have an idea of the dimension of the problem. So dimension of the problem. The number of nodes is simply the size of the element of the nodes matrix in direction 1, so the number of rows, and the number of elements is the size of the elements matrix in direction 1. So as you see, the number of nodes of the structure is 10, the number of elements of the structure is 17. First thing to do when you are building your own finite element code is to build the stiffness matrices of all the elements which are composing the structure. Now, the truss is the simplest finite element you can encounter in your adventure in the finite element world. It has stiffness matrix like this one. Let me take an element here. So this is the truss element. It has two nodes. You can displace each single node in x or y direction, so it has a total of 4 degrees of freedom, and this is why this matrix has 4 columns and 4 rows. If you displace y node or j node in a direction that is perpendicular to the element, so in the y local direction, the element doesn't produce any force. And this is why you have here a row full of zeros and again another row full of zeros. Because if you displace one of the two nodes in the y direction that is indicated here, you produce no force. Instead, the only way you have to produce force with a truss element is to displace either I or j node in the x direction. When I'm talking about x or y direction, I'm referring to the local direction. So the passage will be build the stiffness matrix in the local reference frame, so a reference frame that is oriented as the element is, then pass to a global reference frame that is represented here with the capital X and capital Y letters, with the rotational matrices. But let's start with the local reference stiffness matrix. So in order to build the local stiffness matrix, or better, let's call it global, element stiffness matrices, we have to use a for cycle that will run through all the elements. And the first thing to do is to take any element and the nodes that are composing the element. So for me, node 1 will be elements in position YY, column 2, and node 2 will be elements in position YY, column 3. In this way, at each iteration of the cycle, I know which are the two nodes, node 1 and node 2, that are composing, that are defining the elements I am studying in this iteration of the for cycle. Then we extract the coordinate x of node 1, that will be nodes in position in row n1, column 2, and the coordinate x2 of node 2, as well as the y coordinates. So y1 will be node 1, column 3, and y2 will be node 2, column 3. Then we can calculate the inclination of the element. So alpha of the element II will be a tan 2 of y2 minus y1, comma x2 minus x1, and the length element length of the element II will be the square root of y2 minus y1 squared plus x2 minus x1 squared, in such a way that the stiffness matrix of the element in the local reference frame is EA over eleng times 1 0 minus 1 0 0 0 0 and minus 1 0 1 0 0 0 0. That is this expression here. Now let's initialize some stuff here. So EA, I initialize it to 1, but you can choose any value you wish, and this is just a constant. This is the product between the Young modulus of the material times the cross-sectional area of the element. If the elements have each one a different cross-sectional area, you can put EA inside the cycle to update the value of the area at each iteration, but I think that in most cases the product between E and A is constant, so it's fine to have it outside. Then initialize alpha that will be a zeros of number of elements, comma 1, as well as eleng is the same stuff here, so it's initialized as a vector of zeros, while the k element in the local frame is a zeros of 4, 4, and elements. So it's a multidimensional arrays in which you have rows and columns equal to 4, and the third dimension is the number of elements. And as you see, we have built the stiffness matrix in the local reference frame for each of the 17 elements that are composing the structure. Again, to build this matrix, the formula is this one. This is the stiffness matrix of a truss element in its local reference frame. Now we have to pass, let's use these slides here. I'm sorry, they are in Italian, but these slides present the rotation counterclockwise of a bidimensional coordinate reference system. So suppose you have an XY system and you rotate in a counterclockwise sense this system, and you have a point P here. If you draw the original coordinates of point P, that are the blue lines, and the new coordinates that are the dashed orange lines of the same point P, and you write some basic trigonometric relationship, you get the relationship between the old coordinate system xy and the new coordinate system. Since the truss is composed by two nodes, each of the two has two coordinates, the rotational matrix will be the repetition of this single brick. Let me take it here. So you see here that CS minus SC, CS minus SC is repeated twice, because the first two rows rotates the coordinate of the I element. The second two rows, so the third and the fourth row, rotates the coordinate of the J node. Okay, so basically the fundamental brick is this one. Since you have two nodes per element, you have to rotate 4 coordinates in total, 1, 2, 3, 4, and therefore you have to repeat the fundamental brick that rotates just 2 coordinates 2 times, and you get this. So this is the rotational matrix. Let's implement it here. So let's define C as cosine of alpha E and S as sine of alpha E. Then we define the rotational matrix as CS 0, 0, 0 minus SC 0, 0, 0. Then we have 0, 0 CS, and last row is 0, 0 minus SC. So it's CS minus SC. Let me check. CS minus SC, CS minus SC, CS minus SC. Okay, so the element stiffness matrix in the global reference frame, let's initialize it to in the global reference frame, will be all rows or columns position II of R transposed times the matrix in the local reference frames times R. Now this expression R transposed times K times R is this expression here, and comes from the equivalence of these two vectors. If you let's say apply a linear transformation to the point P in the XY frame, it must be equal to the application of another linear application a linear transformation in the x prime, y prime reference frame. Since they must, if from this equivalence you get this common expression, that the transformation matrix, you can see the stiffness matrix as a transformation matrix in the rotated, or let's say in one of the two reference frames, is equal to the same application matrix, the same transformation matrix K, rotated, pre-multiplying by a rotation matrix transposed and post-multiplying by a rotation matrix not transposed. I mean, this is basic linear algebra. This is not the topic of this lecture. Okay, let's see if it works. Yes, so the stiffness matrix in the global reference frame, now you see that it is a full matrix. Instead, the local one has many zeros. The global one is instead composed by square full matrices. Okay, now let's assemble the global stiffness matrix of the structure. Let's initialize it with a zeros. So the structure here has 10 nodes. You know that each node can move in x and y direction, so the total number of degrees of freedom of the structure is twice the number of the nodes, so it's 20. So let's define the potential degrees of freedom of the structure are 1 to 2 times nodes transposed, because I want to work with the column vector. So this vector, the potential DOF vector, potential DOF here, contains all the possible degrees of freedom of the structure. Some of them will be actually degrees of freedom, some others will become degrees of constraint. Then, how to assemble the global stiffness matrix of the structure. We have now the stiffness matrix of all the elements composing the structure in the global reference frame. We have to link the degrees of freedom of each node to the global degrees of freedom of the structure. So suppose this is node 1. Node 1 will have 2 degrees of freedom that will be in the global structure degrees of freedom 1 and 2. Suppose this is node 2. Node 2 will have 2 degrees of freedom that in the counter of the global structure will be 3 and 4. Suppose this is node 7. This node will have 2 degrees of freedom that in the global structure will be 13 and 14. So the degrees of freedom of any node is 2 times the number of the node minus 1, and I'm writing here 2 times the number of the node. So for example, node 10 will have as degrees of freedom 19 and 20. So this is the point that you have to be clear in your mind to assemble the stiffness matrix of the structure. So in order to assemble the structure, let's set up another for cycle for II that goes from 1 to the number of elements, and again take the nodes that are defining the ith element of the cycle. Then we build the LDOF vector that, as I told you, will be 2 times n1 minus 1, 2 times n1, 2 times n2 minus 2, minus 1, sorry, and 2 times n2. In such a way that, let's transpose it, in such a way that if, for example, II is equal to 2, the degrees of freedom of this second element in the global frame will be 3, 4, 5, 6, because it is formed by n1, that is the second node, and n2, that is the third node, as is written here. So the second element is composed by node 2 and node 3, whose degrees of freedom are 3, 4, 5, 6. Okay. Then we define a logic vector, so logic vector, that is the result of the function isMember of potential doff, comma L doff. So basically, logic vector, where is KL, contains 20 elements, which is the total number of potential degrees of freedom, and has 1 if the element I am considering contains let's say the degree of freedom associated to the row. So since I'm considering now an element which corresponds to the third degrees of freedom, it has 1. Since the 10th degrees of freedom is not a member of the element I am considering, I have 0. This is the function of the logic vector. Now the logic vector puts in relation the elements, the degrees of freedom of the element I am considering with the degrees of freedom of the total structure. So if I define the K matrix, I can say that the K matrix in position logic vec, so in the element, only the elements of the global stiffness matrix which are associated to the degrees of freedom of the current element must be updated, not overwritten. So the previous existing values must be added up to the current kelGlob, all rows, all columns, II, in such a way that the final degrees of the final stiffness matrix is a matrix like this one, in which you have 20 elements that corresponds to the number of degrees of freedom of the structure, and the single stiffnesses for each couple of rows and columns. Okay. Now we have to define external loads and constraint. Let's look at the original structure. So the original structure had a hinge here, a roller here, and a load here. This node must be constrained in both x and y, this node just in y, and here I must apply a load in the negative y direction. In order to find the number of these nodes, so the degrees of freedom associated to this node, I am starting to draw the structure. So before defining the loads, let's start to draw the structure. So drawing of the structure. Let's initialize a figure, then plot the first element, which is nodes element 1, 2, 2, and this is the x coordinate of the first node of the first element, and this is the coordinate x of the second node of the first element. Then we add here a 3, so the y coordinates, k solid, handle visibility off, line width 1.2, and 4, II equal to 2 to number elements, and let's update 1 with YY, yy, yy. Of course I have to add a hold on, otherwise it doesn't work. That's it. I extracted the first iteration from the for cycle because I want to plot the first line, then add the hold on, and then plotting subsequently all the other stuff on the same figure. This is, let's say, the way I generally work with figures with many lines on them. Then we add the nodes. So basically we add a second cycle for II that goes from 1 to number of nodes, and we have plot nodes II, 2, nodes II, 3, so xy coordinate, mark, let's define the marker as KO, then marker face color, let's set it to white, and the size, let's put it equal to 5. Of course, delete visibility also for this, handle visibility off. Okay, in this way, when I activate the legend, I will not see any of these lines inside the legend itself. So this is the structure. Add the labels for the nodes. In such a way we are able to identify the nodes with precision. So text, let's put it let's see, back. Why it doesn't like this? Okay, let's use. Who cares? I don't understand what it doesn't. Does it like it? Nope. So what's the problem with you? Yeah, of course, the function was wrong. So, okay, let's add, for example, a background color. White. Okay, so we see that the hinge is on node number 7. The load must be applied on node number 3, and the roller is on node number 10. Now, of course, if I would have written by my own these two matrices, I would have known which node was let's say the order of the nodes. So I would have known from the beginning that this was node 7 and so forth. But I am using these matrices derived from Abacus, and I don't know in which order Abacus put the nodes and the elements, so I have to plot the structure and find the right labeling. So this is node 7, node 3, and node 10. So the constraints, degrees of constraint, vector degrees of constraint will be degrees of freedom 13, 14, and 20. 13, 14, and 20. And the vector of X load will be simply 6. Because the external load acts in the vertical direction of node 3, that corresponds to the 6th degrees of freedom. Okay, now let's define a logic vector that contains the degrees of freedom, and a logic vector that contains the degrees of constraint. So logic const is simple, is member of potential dof comma v doc, and as you see here we have 1 if the degree is a constraint, 0 if not. Instead the logic free is the opposite. So let's look for tilde, Matlab tilde here. Okay, logic free is the opposite of logic const. Okay, let's now solve the structure. Oh, sorry, we have to define the vector of external forces. So f is zeros of 2 times nodes, comma 1, and f in position vex load is equal to minus 0.01. So we apply just an external force of minus 0.01 in direction y on node 3 here. Okay, now let's run the code. Okay, everything works. Solve the structure. X will be simply equal to k in considering just the degrees of freedom divided by the f in the position associated to the degrees of freedom. And as you can see, we have obtained the vector of displacement. It has just 17 values because these are the displacement associated to the degrees of freedom, which are not only 17 out of 20. In order to get back to the right size of 20, we define a disp vector that has size 20, and in position logic 3 we put the x values. So displacement is now a 20-dimensional vector in which we have zeros where the degrees of freedom is actually a degrees of constraint, and a number, a real number, otherwise. Now, for let's say the way that this structure are schematized, the degrees of freedom are always alternating x and y direction. So here you have x displacement, y displacement, x displacement, y displacement, x, y, x, y, up to the end, x, y. We have to divide the x displacement from the y displacement because I want to sum this displacement to the original coordinates to get the shape of the deformed structure. So the point is now divide this displacement in x and y component, sum them to the original coordinates to get the deformed coordinates. Okay, so x disp will be simply displacement from 1 with step 2 to 2 times nodes minus 1, and y disp will be disp from 2 with step 2 to 2 times n nodes. Both these two vectors should be 10 in size. Let me check. X disp, yes. And so we can compute the deformed coordinate as nodes, all rows of columns 2 and 3, plus x disp, comma y disp. And here you have a vector, a matrix actually, containing the deformed coordinate that are the original coordinates summed with the displacement computed from the solution of the structure. Let's plot this deformed structure. So let's suppress for a moment, and actually forever, the labels of the nodes, and add the deformed coordinates, the deformed elements. So now I want to run from, let's say, 2 to the number of elements, in which now the def core takes the place of the node coordinate. Now the column is the first one because we have just 2 columns for the x, and is the second column for the y. Let's use a line different from the previous one, and let's add the external plot to add a legend. So here the cycle is running from 2 to the number of elements in such a way that the first one here, I use it to add a legend. Display deformed structure. Let's see if it works. There we are. You see that displacements are congruent with what you can imagine by looking at the structure. So here you see that the way the structure is loaded, the way it is constrained, is perfectly coherent on the result we have obtained. Let's add here the legend. So you see it appears now the formed structure, but I want to remove box of position northwest. I never recall if position or location is the right one, so the right one is location. Okay, so now the location of the legend is northwest. Add a title, Truss structure, x label is x coordinate x, y label is a coordinate y. Now last thing to add is the arrow that represent the loads. In order to add this arrow, you can use the quiver function that takes the components, let's say the origin of the arrow, the components of the arrow, and is very useful to represent loads on this type of plots. So let's add it just before the plotting of the nodes. I plot the nodes as the last one because I want them to not be covered by the truss, by the lines. If you plot it as the first, they then get covered by what you plot next. So here I add a quiver that we told previously is acting on node 3. So we have nodes 3, 2, nodes 3, 3, 0, minus 10, that are the component of the arrow. Let's hide it from the legend. No, actually gave it a legend name, so display name external load, and let's see, that's it. This is the final structure with external loads also presented. This is the code that allows you to study any two-dimensional truss structure. You simply have to modify the matrix of nodes and the matrix of elements. Everything else is can remain constant. The other thing you can do is to update the value of the stiffness modulus E times A. Also here the way the degrees of constraint and the external loads are implemented requires to know on which nodes they must be applied. So you have also to update these parameters, the constraint and the external loads. The external load, of course, can be also a vector. I mean, you can have many loads applied in different positions. Recall that truss cannot withstand bending, so you must be sure that the structure can deform in a way that is producing a force in a way that it's absorbing energy, otherwise the stiffness matrix will be singular and the code doesn't work. But it doesn't work because it doesn't work the physics of the problem, not because the code is broken. And that's it. If you change the scale of the structure, that is, if the coordinates of the elements are quite different, probably also the scale of the arrows that represent the loads must be updated. Here I have used a magnitude of 10 that is good with respect to the size of this structure. If the structure that you draw will span from 0 to 2000 as x, probably you will have to update accordingly also the scaling of the arrows that represent the load. But I mean, this code can be complicated as much as you wish. You can implement controls on the type of the data. You can implement also the way the plot is scaled in such a way that the absolute dimension of the coordinate is no more a problem. But the core of the finite element solution of a truss structure is what we have seen right now. So I think that is done for this lecture, and see you next time.